Welcome to an unequal sloped roof math problem. While it might sound difficult, it really isn't all that tricky. So I'll walk you through the whole process, front to back, and hopefully that helps you out. Okay, so let's have a look here. We have a roof, we have a major roof, so that is the main big roof, and then we have a minor roof. They're unequal sloped, which means most of them, and you can see here in this plan view that the ridges meet, which means the ridges are the same height, which means the total rise of each roof will be the same because they all meet at the same spot at the peak. The drawing is not to scale, just so you know. So let's see about our measurements here. We have a major roof span of 10.2 meters. Whichever level you're in, this should be getting to be very easy to just turn that into millimeters. 10,200. And everything in roof math here will be millimeters. So I won't be writing millimeters in everywhere to not make it be so clustered. We have a major roof slope of 200 to 250. Roof projection, that's right here, that's 0.4, so 400. So that is the horizontal projection of the fascia. Then we have a minor span, let's have a look, 5.4 meters, so 5,400. As you might remember, we don't use the span in roof math, but we use the run. So 5,400, you're welcome to pull out the calculator, divide it by 2, gets us 2,700 right there. And for the 10,200, gets us 5,100 right here. 5,100. And then we'll have our 400 projection as well. Our minor slope, we don't have that one yet, but we will get back to that in a little while. So let's have another look here at this funky N shape, which really is just a couple of triangles. At the peak, this is where the ridges meet. So this is the major roof ridge and the minor ridge. This right here is the major common rafter, major common. So that's the 5,100 to here. And we will be adding the the fascia here, or the projection as well of 400. Then this right here is the minor common. And incidentally, you can see that this minor common is actually parallel to this portion of the ridge, which means this will also be representing the minor common. And you'll see why that's important in a little while. And this right here will be the valley run. Pop in valley. And the important thing to note here, this is a plan view, right? We're just looking straight down, which means these are all runs. This is a run, this is a run, and this is a run. And maybe you can already tell this is a nicely looking triangle with a 90-degree right here. So we'll be able to use Pythagorean on this in a little while. Okay, so that is our roof. Then this is going to be the setup. I drew this out previously and nicely on the computer as nicely as I could, but with practice, this will take you about maybe a minute to actually draw out on just a sheet of paper or into your notebooks. Highly recommend that you do that. So just pause the video, draw these all in, and then I'll explain what everything is. But it gives a really nice overview of what we're doing. Important to note here, we'll have an elevation view of our major common, right? We're looking from the side. We have an elevation view of the minor common. Then we have an elevation view of the valley. And then we have a major to minor run ratio in plan view. And you can see this little triangle very much looks like this little triangle in this one right here. But we'll get there in a minute. Then we have a bunch of questions, things that we need to find out. So for the major common, We're going to want to know the total run, total rise, the total line length, the overhang, and the difference in the height of wall plates. If you remember from any theory class, is that to ensure that the fascia projection or the projection here is the same and that the fascia actually is even across the whole house, the minor roof walls get raised. So we'll have to find out by how much they need to be raised. Then we're figuring out the same things for the minor common, really the same things for the valley, including the projection, because we don't know that yet. And it's going to be different than the 400 and the offset. The offset, and I'll show that to you in a more detailed drawing in a little while. You can see right here that all these rafters meet at an inside corner at the fascia, but here at the building, like at the walls, the valley doesn't actually run right over top of the corner. That's totally fine. It's not a big deal. It's supposed to be like that. But this right here is that little offset from the corner to the valley. That's what we're trying to find. So that when you go to lay out this roof, you can actually lay it out properly. Okay, I'll try to lay these out in a way that makes sense. Okay, so do we have the slope for our major common? Yes, we do. It was given to us, 200 to 250. 200 to 250. Perfect. I'm a visual person, so I like to just draw this in a little rise to run triangle, right? For every run of 250, that's common for metric, the roof rises 200. Now, I like to do the slope gain factor, SGF, where we work with a base 1. If this is unfamiliar to you, I'd really encourage you to check out one of my other videos, which is the Intro to Roof Math and SGF, because that's really going to help you out. Makes the process much easier. So what happens is we want to get to the base 1. So 250 divided by itself, divided by 250 gets us 1. And to get the rise portion, 200 divided by 250 gets us 0.8. 0.8. This is the same ratio as a 200 to 250, except we have a base 1. And the number that we're really trying to find is the hypotenuse of this triangle, which is the slope gain factor. So 0.8 squared plus 1 squared equals second function 1.28, and we can round that to 1. So 1.281. Wonderful. We need to find the run. Technically, we already have it. Any other roof, the run of the rafter is just from the ridge to the walls. But because our walls between the minor and the major roof are uneven, we have to extend our total run to include our projection. So to the outside of the fascia, because that is the only point where we can actually compare all of these triangles to each other. So from our drawing, we have 5,100 as the run of the major, 5,100. So I'm writing that on the inside as to not get confused. We have a projection of 0.4, so that was the 400 millimeters. Write that on the inside here. And then we add them together to make the total run of that rafter of 5,500. So in the drawing, that's from the ridge all the way to the outside. This is 5,500. It's a terrible 5. Sorry. There you go. So that's 5,500. So there are a few things that we need to figure out. We found the total run, so that's great. How about the total rise? Well, the way to find the total rise is to take our total run and multiply it by our unit rise factor. So 5,500 times 0.8. And that goes to the very bottom here, right? So 4,400. That's our total rise. Now, how about that total line length of the rafter, which means all the way on that sloped, once it's sloped and installed, how long is the theory length? Well, this is where the total run and the slope gain factor comes in handy. So 5,500 times 1.281, 7,046. We also wanted to find the tail. So same thing, we take our run of the rafter, 400, times our slope gain factor, 1.281, gets us 512. For layout purposes, this question isn't really asking for it. It's asking us for the total line length. But I like to find the line length from the ridge to the plate anyways, because when you go to lay it out, this is a number that you're going to want to pull out on your tape measure. So that's our 5,100 times 1.281, 6533. Right, and then just to double check, plus 512 gets us pretty much there. So 7,000, that is 7 meters. To be within a mil, that is perfectly acceptable. And, I challenge you to cut it that well. So to find our slope length, we use the slope gain factor. Now, should you come to a place where you forget how to do that, once you've found your total rise, this is just a triangle, right? So you could use Pythagorean as soon as you have two of the numbers. If you remember how to get the total rise, wonderful. You can use a squared plus b squared equals c squared, right? Or if you remember how to get your actual slope length at theory line length, and you don't remember how to get your total rise, well, you could say c squared minus b squared equals a squared. There are many ways to go about any math. And really, I'm just showing you one, maybe two of them, but there are always many ways to go. Okay, there's one more thing that we can figure out here for our plate difference that we're going to try and find out. This right here, this is a unit or a rise factor, right? We have that little triangle of a run of 400, the hypotenuse, the overhang is 512. So again, you could say c squared minus b squared equals a squared. Or you could say your run multiplied by your unit rise factor will actually get you the rise number here. So 400 times 0.8 gets us 320. So what that means is from our plates to the bottom of the fascia is 320. The number here for our minor common is going to be different, and the difference between the two of those is going to be the difference in our plate height. I think we've got all these figured out for the major commons, so let's have a look. Total run, 5,500. Remember, unequal roof, it's the only one where you're including the tail or the projection as well. Total rise, 4,400. Total line length, so that is all of it, 7,046. The overhang, 512. Most terminology is that projection is on the flat, on the horizontal, and that overhang is on the slope. Difference in height of wall plates, we don't know that one yet, so I'll leave that out for now. And we could move on to the minor common. So very exciting, moving along swiftly here. Well, let's see. We don't have that much yet. Do we know the slope? Do we know the total run or the total rise? We sort of do. Let's have a look. So we had the 2,700 was from the ridge to our wall plates. So that is right here, 2,700. And then we know that our projection was the 400, same as the major common. So we could pop that in there, add them both together, gets us 3,100 for our total run. Now, because this is a plan view, it is an unequal slope roof, and the ridges meet at the same spot here. It means that they have the same rise, right? If the ridges didn't meet, you would have that a supporting valley and then a supported valley, and at that intersection is where the ridge would meet, but they don't. They all meet, which means same total rise, which works well for us. So that 4,400 right here is a 4,400 right there. Now, usually slopes are expressed in 200 over 250 or 180 over 250 or in imperial 512, 1212, etc. But really what that is a rise to run ratio. A rise to a run ratio. So while these numbers might look a little bit unfamiliar, that is exactly what the slope is. We just don't use them like that usually, but that's fine. It gives us a rise and it gives us a run. So from that, we can figure out our slope gain factor again. And just so you can see it, right? We can draw the same triangle, 4,400, 3,100, and it doesn't look any different than any of the other numbers that you're usually used to seeing. So our slope gain factor, we always turn it into a base 1. So 3,100 divided by 3,100 gets us 1. 4,400 divided by 3,100, that's what we need to find out. 4,400 divided by 3,100. 1.419 gets us the rise per 1 unit of run. And you can already see the major was 0.8, this one is 0.419, so it's quite a bit steeper, which makes sense. And we want to find out our slope gain factor. So a squared plus b squared equals c squared, second function, 1.736. Perfect. So that slope gain factor is the number that we're using to find our total line length. That is my preferred way, but because we know our total run, total rise, we could also use Pythagorean should you forget how to do the slope gain factor. So 3,100 times 1.736 gets us the total line length of our minor common rafters. So what is that? 5, 53, let's call it 82. 5382. Wonderful. How about our overhang? Same thing, 400 times our slope gain factor. 400 times 1.736. 694. Wonderful. For layout purposes, like I mentioned, I like to figure out the line length from the ridge to the plate as well so that we know where to mark out our bird's mouth. So 2,700 times 1.736. 4687 right there. And just to show you that I'm not out to lunch, right? We use our total run times our slope gain factor to get our total line length. Well, let's see what happens if we did our use Pythagorean. So a squared plus b squared equals c squared. Function 5382. 5382. There you go. Right? Always many ways to roam, which is awesome. So in the shop or in at work, you might have to actually go and lay out a minor common rafter. 4,400 and 3,100 is going to be really difficult to locate on your framing square. So if we wanted to use that same something to 250, because that is the common way to lay out roof rafters, we want 250 on the run side. Well, could we do ratio and proportion? We could, right? So what we want to find out is that rise number. So the representation of 4,400 or that 1.419 compared to the 250. What would that be so we can actually lay it out? So cross multiply, what we want to know is x. So we'll call that x. Rise over run, x over 250 equals to 1.419 over 1. Can we figure that out? Absolutely, right? 250 times 1.419 and divided by 1 gives us 3, let's call it 55. So this right here will be 355. So if you wanted to lay it out with a framing square, you would use 355 on the rise and 250 on the run. And just because we want to keep things even, we could draw in the same thing for our major rafter, major common, and we already know that slope was 200 to 250. But that way you already have it all taken care of. Cool. Now, plate difference. We're still missing that one number. So we want to know the rise of that little projection and overhang triangle. We could do c squared minus b squared equals a squared, or the roofing way, which is your run of the rafter, 400 times the unit rise from that slope gain factor triangle, so 1.419. 560, it's called 568. 568. So that is the drop from our plates to the bottom of the fascia. So 568 of our minor minus 320 of our major, because we just want to find the difference, right? 568 minus 320 gets us 248. So that means that the minor roof walls are 248 millimeters higher than our roofs that support the major, so than the walls that support the major roof. That's what that means. So that if you were to go and build these, you know that to build the minor portions, so these walls here, 248 mils higher. Okay, I believe we figured out a lot of things here for our, oopsie, sorry, for our minor common. First difference in wall plates, 248. Total run, 3,100. Total rise is the same, right? Which is cool because it's also going to be the same for our valley rafter because they all meet. Total line length, 5382. And then overhang is that 694. Boom. Total rise for the valley. We already know that because they all meet, which is great news for us. Because that's where we need to go next. We need to find out our valley. And for that, we're using our valley elevation view, and we're also using something called the major minor run ratio. So this is plan view. This is just looking down, just like we look down on a plan view on our plans. So there is one thing that we already know about the valley, which is our total rise of 4,400, because all the rises are the same. We need to find our total run. We don't know that yet, but let's have a look here. We have our major common rafter, 5,500, right from the ridge to the outside of the fascia. We have our minor common run from the ridge to the fascia of 3,100. It's 3,100. And because the common rafter in plan view is parallel to the ridge, we're just gonna use that number up here. So we can draw ourselves this beautiful triangle. And here, maybe I can draw it in red. Does that show up? Not really, so I'm not gonna bother. But this right here. So we're in plan view. So we have the run of the major, we have the run of the minor. Well, this very much looks like a triangle we could solve, couldn't we? This looks like Pythagorean. So on our worksheet, this is what I've drawn out. We have our major common rafter run, which is 5,500. We have our minor common rafter run, which is 3,100. And you can see, right, the major runs north to south, sort of, and the minor east to west. Same as on here. That way everything is easier to keep track. And our valley is the triangle or the hypotenuse of that triangle. So, okay, so can we figure this out? So this is the valley run. And we are using the numbers including our tails or the projection because those are the triangles that we've been comparing this whole time. So let's see. Let's Pythagorean this up. 3,100 squared plus 5,500 squared. Second function, we've got 6313. Okay, awesome. So 6313. This is what we just figured out. That the value run is 6313. 6313, and it makes sense, right? 3,155, one is shorter than the other, and our hypotenuse is the longest. Groupie. Now, do we know a slope? If you remember from our minor common, a slope can be anything. All we need is a rise to a run, which we now have. So we have our total rise of 4,400, and we have our total run of 6,313. So I can draw myself that triangle just because I'm a visual person and I like that. 6,313 and 4,400. And then we also do our slope gain factor triangle with our base 1. 6,313 divided by itself gets us 1. 4,400 divided by 6,313 gets us 0.697. And again, when you think about it, steep, much steeper, least amount of steep, right? Because the valley travels the longest, so it needs to be less steep so that for every same amount that it travels, it doesn't rise quite so much so that they actually all meet together. So that's great. That's just a thing that you can check because should you punch something in wrong and end up with 1.697, then you'd be steeper and then none of this would work, right? So it's just a thing you can double check for yourself. So let's find out that slope gain factor. So 0.697 squared plus 1 squared. Second function, 1.219. Cool. Alrighty. So now, can we find out more things? I would think so. We can find out our total line length, right? Total run, 6,313 times our slope gain factor, 1.219. 7,696. If you forget the slope gain factor, write Pythagorean a squared plus b squared equals c squared. Excellent. Do we know our run for our projection? Our projection for the common rafters is 400. But if you remember, this is 400, right? The projection here, and this is 400, which makes, this up here 400, which is parallel. So that triangle, like that hypotenuse there, it cannot possibly be 400, right? So this is something else that we would like to figure out. And what we're trying to find out is the run of the valley projection. So this right here, run of the valley projection. That's what we need to find out. And because this right here is tiny and difficult to see, whoops, that's upside down. I've drawn it up for you in big. So just have a look so you can see what we're doing. So it's the valley offset detail. So this whole corner is this corner right here. So have a look. This is the outside fascia. So that's that outside corner, the outside inside corner. This right here is the building line, the plates. That's these ones, right? And then this right here is our valley rafter, right? That's our valley rafter right here. So the whole thing is the valley. Oh, it's terrible writing. Sorry. There we go. So let's have a look then. If the whole thing is the valley, what would this little chunk be? Could that potentially be the run of the valley, the run valley projection? It could, right? So run of the valley projection, because this is all done in plan view, just like this up here, right? Just in greater detail so we can actually see what we're doing. So what was this measurement? This one, maybe I'll use a different color this time. What was that measurement? Well, this is just our projection, right? So this would be 400. And could we compare this to something else? Potentially. Look at this again, right? This right here, 400 going this way. So 400 right here. And that could be compared to the major common rafter or the major projection. So we'll call that the major projection. And this little fella right here, what does that compare to? Right, this little guy, which is this little guy, that is very much comparable to the minor common rafter. Hope you guys see that, right? And then the run of the valley projection here, that's comparable to the big valley. So we're just working with the same pieces, just in smaller with different numbers right now. But we can put in minor right here, just to show off that's what we're doing. Okay, so what we want to find out is really the run of the valley projection, but we don't know that yet. And this is the hypotenuse of that little triangle. We also don't know what the minor one compares to here yet. So we could call that X for now. We do know that this is 400 because it's the projection and it's comparable to the major rafter. So let's see how we can help that. This right here is the run of the valley projection, right? This hypotenuse right here is this hypotenuse right here. This is comparable to the minor. Maybe I should be using colors. And this is comparable to the major. So for this little triangle, we know that the major is 400. So we can pop that in there. That's great. We want to find the minor first, which was blue, which we had called X. So could we do ratio and proportion? Because we already have one number, we're looking for another one, and we're comparing them to the minor and major runs. So I would say, right, we have a minor run here of 3,100 and the major of 5,500. So I'm going to say, yes, that we can say major over minor. So major is 400 over X, and we want to compare it to the big boys. So the major run is 5,500 and the minor is 3,100. So now all we need to do is cross multiply. 400 times 3,100 divided by 5,500. Which gets us 225. X equals 225. Amazing. X equals 225. Wonderful. Well, now this looks a whole lot like Pythagorean again, doesn't it? Could we just use that? I say absolutely. So 225 squared plus 100 squared, 459. We can use that. 459, which is the run of the valley projection, which is just this little part right here, 459. This guy right here. If we look at our roof, the run of the valley projection is this one. Super duper. And because it's the hypotenuse, it does make sense that it's bigger than the projection of the others, right? Yoo-hoo. Cool. So there's something called the valley offset that we talked about earlier. The valley offset is actually this one right here. Ooh, this one's going dead. Get a little color. Okay, so the valley offset. How far is the valley actually away from the corner, that inside corner of the building? Well, we knew that our projection from the major and the minor is 400. This is the major projection. Well, this is the minor projection. And that was also 400, right? Because the projection, the whole point of this is that the projection is the same all the way around, right? So this here is 400 as well. Knowing that means that this up here is also 400, right? Because I just wrote it down here, so it's not also clustered. So if this is 400, and we know that this little chunk here is 225, can we figure out this part? Absolutely, right? So 400 minus 225 gets us 175. So that's this right here, 175. From the corner to the valley rafter, the offset is 175, right? We just take the full projection minus that 225 that we figured out as part of that projection and run of the valley triangle. That gives us the leftovers here. And I realized that the 225 does not look like the 175, and that only has to do with my lack of expertise in drawing things on the computer. So, sorry, but hopefully you can still see it. So 175 right there. So valley offset was the 400 minus our 225 gets us 175. Okay, groovy. Now we can just deal with the valley rafter to finish that off. We found our total line length. Can we find our overhang? Well, yes, we have our 459. 459 times our slope gain factor, 1.219. Let's call that 560. 560. And if we wanted to find our run, so we can find out this guy, of course we can, a couple of ways, right? So 6313 minus 459 would get us 5854, just the run to the plates. And then to find the line length to the plates, we can either just say 7696 minus the overhang, 7696 minus 560, 7136. Or if we wanted to use the slope gain factor, we would just use this portion of the run, 5854, times our slope gain factor. 7136. Boom. Nice way to double check. Let's have a look. Can we write down the rest of our numbers? Total run of the valley, 6313. We had the total rise already, or 4400. Total line length, 7696. The projection, 459, which gives us an overhang of 560, and our offset of 175. Boom. Done. Okay, so let's do a quick little recap. This layout I find super helpful because everything is on one page. You don't need pages and pages. If this is all brand new to you, you are most welcome to write every little calculation out on a piece of paper and put some words to it so that it makes more sense to you, that you can look back on it and understand what it is that you're doing. Ooh, and I'm sorry, one thing that we didn't do was find out our how we would lay this out. Sorry, let's add that as well. Because we would want the 250, right, to use on our framing square, and we would want to find out the run because this is a funky little slope as well. So let's see if we can do ratio and proportion. We want 250 at the bottom, which means our x here is at the top, x over 250. And then we can use our rise and run ratio right here to compare to. So 0.697 over 1, 250 times 0.697, and divided by 1, but it stays the same, right? So 174. Perfect. 174. Boom. So now we also know what numbers to put on our framing square. Okay, yeah, quick recap. The total run of an unequal slope roof always includes the tail or that projection, right? And to find our total line length, we take our total run and we multiply by our slope gain factor. That is the same for all three rafters. Because they meet at the same height at the ridge, we know that the total rise is the same for all of them, which is the basis of finding out the slopes for the minor common and the valley, right? Slope is only ever a ratio from a rise to a run. Because we know the total rise and the total run, we can use that to find our slope, to get our slope gain factor, to then fill in the blanks for the rafters. We needed to find the rise, or really it's the drop of the plates, or however much the minor common rafter plates or walls need to be raised. So that was the run of the projection times our rise factor here. That gets us this rise value, that rise value, right? So it's always a run times a rise value when you have that base 1 that gets you the rise of that triangle. Should you forget how to do it, it's Pythagorean, right? C squared minus b squared equals a squared. We use some ratio and proportion to figure out what numbers we would put on the framing square so we could actually lay out these rafters. And then we used, to find out the numbers for our valley, we used the run numbers. So the minor common run and the major common run from our roof, right, that we can see here. We just recreated that triangle and drew it in here so it's a little bit more clear to find out the run of the valley. And then the last thing we needed to find out was the projection right here, where we did the same kind of work with the triangles, just in that little corner down here. And that's where we use the kind of the more detail, where we use the projection and we compared the projection from the major to that little chunk of the minor to find out what that X number is, to then do Pythagorean to find the run of the valley. Once we add the run of the valley, we can actually find the overhang. So I hope that makes sense and is helpful. And I'll see you next time.